Okay, so we're continuing with our thermochem unit, and we're going to take a look at some more Hess's Law examples. If you did want more of an explanation on Hess's Law, you can check out my thermochem playlist, and you would definitely see a lesson there. So let's start with some examples. So this one we have our target equation, and this is the enthalpy we want to figure out. This would be considered Hess's Law long or mathematical because it's like a puzzle. We have to take a look at these given equations, rearrange them to get to that target. So I'm going to start with that first equation, and I see carbon as a reactant, and it's a reactant on the first one as well in my target. So I'm just going to leave that so far. Now I'm looking at the second equation, and in the second equation, I see carbon monoxide as a reactant, but in my target, it's a product. So I'm going to flip this reaction, but I'm not going to change anything else. So I'm just going to rewrite that first one, the first equation, and I didn't change it, so the delta H is still negative 393.5. The second one that I'm going to flip, I now have carbon dioxide as a reactant, 1/2 oxygen plus carbon monoxide. And since I flipped it, now my delta H would become positive because I need to change the sign. And now this last reaction, the one with water as a gas is on the product side, but I need it on the reactant side. So I'm going to flip that last one as well. Okay, so now because I flipped this last one, I need to just change my sign once again, which I've done. And now we can notice how things will start to cancel nicely. So we have carbon dioxide, just 1 mole of it as a reactant and as a product, so those will cancel. We also have 1 mole of O2 as a reactant, and then if we added this half with this half of oxygen, we have a total of 1 as a product. So those will cancel, and everything I'm left with is my target. So I'll have carbon solid plus water vapor to give you carbon monoxide plus hydrogen. So then my last step is now just to add my enthalpies together. So I just want the molar enthalpy of this reaction. So let's go ahead and put that into your calculator. And 3.0 plus 242. And we're getting the delta H to be positive 131.5 kilojoules. So that's our first one. Again, it's like little puzzles. So we'll just make sure that we take our time and cancel out what we see on the left and the right hand side to hopefully get to our target. Our next equation is another Hess's Law long, and we're going to be doing the same thing. You have your targets, and then we want the enthalpy of this reaction here. So let's start doing what we did on the last one. It's just looking at placement. So we have N2O5 as a reactant, but in my first target, I have it as a product. And the other part here is I wasn't told my delta H on the right hand side, so I'll have to interpret my delta H. So I should know from this first one, if I have a delta H value as a reactant, it would be a positive 15. So now when I take a look at my first reaction, like I mentioned, I need to flip it. So I'm just going to rewrite it N2O5 as a gas to give me N2 plus 5/2 oxygens. And I'm going to just take that 15 out and write it on the side. So if you like it in there, it's fine. You'll get to the same answer. I just prefer to have it with the delta H notation on the side. So that's my first reaction. The second one I'm looking at, I'm seeing water as a reactant, and in the second target, I see it as a product. So this is another one I want to flip. My delta H is written within, so delta H as a product is negative, so negative 286. And now let's flip that one. So now I have water, and that gives me H2 plus 1/2 of oxygen. And I flip this reaction, so delta H is positive 286. This very last one with the delta H again as a product, just to begin with, if I take it out, it would be negative. And now I want to just look at my placement. So I have that 2HNO3, and from that last target, I also have HNO3 as a product. So it's in where I need it. The part here, though, that matters is that this value only represents 1 mole and I need 2. So I'm going to take that second equation and multiply it by 2. So I'm multiplying this whole thing by 2, and that includes your delta H. So that means I'd have only 1 hydrogen plus 1 nitrogen plus 3 oxygens to give you 2 HNO3. And the delta H for this one will be 173 times 2, negative 346. Now let's see how things are going to start to cancel nicely. So you have hydrogen as a reactant and as a product, 1 on each side, so they'll cancel. Nitrogen, 1 as a reactant, 1 as a product, so they'll cancel. 5/2 plus a half would be 6/2, which is divided is 3. So these oxygens will cancel with the 3 oxygen on the left. And now I'm left with my target. I have the N2O5, I have water, and I have 2 HNO3. So now that I have everything where I need it, my last step is just to add all my enthalpies together. So let's go ahead and do that. So I have negative 15 plus 286 plus negative 346. And I'm getting the delta H of this reaction is negative 75 kilojoules. Okay. So that's Hess's law long, where you are just seeing where to place your, from your given equations, which side to put them on. Do you need to multiply? Do you need to divide? And then just remembering how that's going to affect your delta H. Now, the next one I would like to take a look at is now turning into Hess's law short, where if you're using Hess's law short, you are coming up with the equation yourself and then using the enthalpies of formation, which are on page 4 or 5 of your data booklet, and filling it in from there. So Hess's law short, the delta H of a reaction is the product's delta H minus reactants. So let's start by writing out this reaction. So acetylene, you do find it, I know this is really, really small here, but you do find it, which one is it here? Right here. So it also has that molar enthalpy of formation. So I'm going to just write this out. So we have C2H2, and if you're looking at a combustion reaction, right, then you know you're adding in oxygen and your products will always be carbon dioxide and water. Now this one is telling you liquid water. If it is a open system, gas wants to escape, and it would be gas water. And if it's a closed system, it's liquid water. If it doesn't tell you, you could assume gas. Before we go and fill in those enthalpies of formation, we do need to balance. Hydrogen's already balanced. We'll put a 2 here to balance out the carbon. Then we have 5 oxygens on the product side. 4 from the carbon dioxide, 1 from the water. So to make 5 on the right hand side, we're just going to use that fraction, 5/2. So now we have 5 oxygen on each side. Now we can start to fill in the values. So C2H2 has enthalpy of formation of positive 227.4. Elements alone are just 0, so we don't have to include them. On your product side, we have 2 moles of carbon dioxide. 1 mole is negative 393.5, so you'll need to multiply that by 2. And you have 1 mole of water, and it is the liquid water. So just be careful there because there is liquid and water vapor, so we want the one for liquid. So negative 285.8. Now we can total up our products, and if I want delta H of the reaction, it's again products total sum minus reactants. And there's a fancier way to write this with the summation symbol, but this works. So when you're filling this in, so the sum of your product side is negative 1072.8 kilojoules per mole, and we're going to subtract your reactants, which is 227.4, and we get negative 1,302 kilojoules, and this is per mole because there is only 1 mole reacting. So that is our final answer. And in terms of SIGDIGs, because we're just adding everything in, it really depends on how many the question will tell us. Now our very last example is putting a little bit more work together. We are going to start with using Hess's law short to figure out the molar enthalpy of this reaction. It is not a complete combustion reaction, and we know that one because it says it. Also because we see this extra product of carbon monoxide, and you could also see carbon as soot if it's incomplete combustion, but this is where we'll start. So it's asking us for acetic acid. Acetic acid is also in here. You have to just find it. It's a little, again, this is really, really small, but hopefully you have a data booklet. So this first one, we're going to have 6 times negative 484.3. Again, oxygen is by itself, so that has a formation of 0. Then on the product side, you have 10 times carbon dioxide, so negative 393.5. Then you have carbon monoxide, so 2 times negative 110.5. And then you have 12 water as a gas, which is water vapor, so negative 241.8. Now we want to do the same thing we did before. We want to get our total on the right-hand side and subtract our total on the left-hand side, right? Because that still tells us delta H of the reaction is the sum of the products minus the reactants. So if I do that, my sum of my products, I believe, was negative 7,057.6, and I need to subtract my product. So 6 times negative 484.3. Now, when I do this, the value I'm getting is negative 4,157.8 kilojoules. If I want a molar enthalpy for the combustion of acetic acid, that means I want it to represent just 1 mole. But this reaction has 6 moles, so before I finish, I need to divide this by 6, and that's why our answer is negative 692.0 kilojoules per mole, right? Just 1 mole of what's reacting. Now, this next one, asking about how much energy would be produced depending on moles, this is now an NH equals delta H question. And I do again have a video on this that's more specific, and you can go check out the Thermochem playlist on my channel and you'd be able to find it. But just that reminder that this H is a molar enthalpy and it comes from the reaction. And within the reaction, it will look like delta H, but that's the one we're pulling out. And then we multiply it by the number of moles, and that tells us how much energy is released. So I'm going to start with that 10.0 grams and multiply it by the molar mass of acetic acid, which I did calculate already, is 60.06. And then you want to multiply this by your molar enthalpy. So acetic acid's reaction was negative 4,157.8 kilojoules, and we knew there were 6 moles reacting. So notice how your units cancel, grams cancel, moles cancel, and when you plug this into your calculator, you'll be left with the energy released, which is going to be negative 115 kilojoules, and in this one, keeping 3 sig digs because your grams had 3. Now the very last one, asking about the molar enthalpy of the reaction for carbon dioxide. We're still using that same delta H of the reaction, negative 4,157.8 kilojoules, right? What we calculated in that first question. But instead of dividing it by acetic acid, it's asking you about carbon dioxide. So we're going to take that value and divide it by 10 moles of carbon dioxide, and you'll get negative 400 and 15.2 kilojoules. Wow, why was that so hard for me to say? So as always, I hope this helped learning Hess's law long, Hess's law short, and just looking through a few old examples. If there's anything else I can help you with, please leave me a comment and I would be more than happy to do a video. And if you came this long and you found this helpful, please subscribe. Thanks for watching.